So good morning. Today we'll extend the analysis of last time. We started talking about using the state space setup in creative ways. And today we'll use it to wrap up a few loose ends, including some elements that will be useful to you later on in this course, and possibly later on in your career in macroeconomics. So we'll start by thinking about these applications of the state space setup. I call it the AOC because A sub 0 C are the relevant symbols. We'll use it to think about the Kalman filter, which is one way of using time series analysis in a creative way to generate best estimates of unobservable processes that evolve over time here in a stationary environment. We'll use the state space in a decisively important way to think about how to write down a discounted sum of linear quadratic forms in expected terms or under certainty, and to collapse this in a very, very compact way as a function of the state in the AOC setup. And then we'll use that to motivate thinking about a value function. So one way of thinking about these discounted quadratic forms potentially is the optimized value of a problem. It doesn't necessarily have to be the case, but if you can use the state space to think of the policy that is optimal, conditional on the other environmental variables and the value of the state, then you can use that to evaluate the implied value function in the next period going forward, the optimized value. So that's a way of motivating the so-called Bellman equation and dynamic programming. We'll only make a brief mention, but it's still useful to use a linear quadratic setup and the state space to think about the cost of business cycles, if you could measure those on the basis of a linear quadratic setup. Okay. Last week, what did we do? We had a big jump. We moved from thinking about the linear state space model, the AOC model, by applying it to an interesting economic problem, which is Milton Friedman's permanent income hypothesis under rational expectations, which is the application that Robert Hall pushed forward and successfully, in my view, in the 1970s, in 1978 in particular. We'll use that as a way of teaching how to use the Lagrange method. A lot of you have used this already, but just to get everyone up to speed, but also using it in the context of the state space. So it's a very interesting way that I would have benefited from had I been when I was a graduate student, had I taken this course. In the meantime, we've moved much farther along, and we've had a very compact way, which is summarized in Lundquist and Sargent in a very efficient manner, how to attack these problems and using the Lagrange approach. Last time we also talked about a linear quadratic setup and what a linear quadratic form is, what a quadratic form is, and how you can think of that as some sort of maximization or minimization problem in economics and how to interpret it. And we also had some other interesting results involving expectations, linearity of expectations, taking derivatives of expected values, differentiation being a linear operator, meaning that we can actually write a lot of the important first-order necessary conditions in a very intuitive way. But one has to be careful, and also using the law of iterated projections to help us along the way. Finally, we wrote down the solution to the Hall-Friedman problem as a dynamical system using the AOC setup, and we stressed that this particular setup, this particular problem where the representative consumer is choosing consumption optimally, implies that consumption can respond immediately in period t to new information that arrives in period t, which means that as a control variable, CT is not predetermined. It's probably useful to think of it as not just as a control variable, but as a complement to the state space that we've looked at. In fact, given the realization of these unknowns that occur in period T, we can write the optimal policy with respect to consumption as a linear combination of observables in period T. So that notion of writing the optimal policy as something that lies in the subset, in the subspace of the state vector xt is kind of an interesting idea. It also implies that the A0 matrix doesn't have the absolute stability properties that we talked about a couple of lessons ago, but actually it will have a certain number of eigenvalues that are on or outside the unit circle, depending on the number of jumping variables. And in the case of consumption, there was just one, so that there should be an extra eigenvalue that is on or outside the unit circle. This is the so-called motivation for the so-called Blanchard-Kahn condition. In general, rational expectations models in discrete time that have a co-state variables and state variables. For saddle stability, the condition that's very important is the number of eigenvalues of the matrix A0 that are outside the unit circle or on the unit circle has to equal the number of jumping variables. So this will be useful to many of you who go on to use DINAR to study larger systems where the computer program will actually evaluate the eigenvalues of the A0 matrix or some related matrix. Okay. So again, if you want to do well in the final exam, please pay attention to the problem set and the problem sets, because the correlation with the final is quite high. So let's review. The state space involves a transition equation. It involves an observer equation. The transition equation, or the state equation sometimes it's called, is simply the AOC. You need to know A0 and you need to know C. And you need to have these matrices to describe the movement of the state vector through time. So think of AT plus 1 as being a matrix A0 times the previous value. That's a fairly canonical general way of writing down this state vector, which can include multiple lags and a lot of bookkeeping through the A0 matrix. And CT, which is involves the transmission of the current shocks in period T plus 1 into the state xt plus 1. Okay, so we can recall that the dimension of the state vector is n by 1. The dimension of the state, the transition equation A0 matrix, is n by n. It's a square matrix because it's taking the predetermined part of xt in period t into period t plus 1 in a certain way. So the coefficients of the model will be embedded to a large extent in A0. And then C is you could call this a transmission matrix, which involves transmitting shocks summarized in the omega vector, which need not have the same dimension as the state vector, into said state vector. So think of C as being an n by m matrix. M could equal m could equal n, but it doesn't have to be the case. And omega is an m by 1 matrix. So m could be equal to 1. You'd have a single shock driving the entire macroeconomic model, or you could have an overdimensioned number of shocks impinging on the model, and C would have to be correspondingly made to be conformable with that setup. Okay, so C has to be n by m. That's the state. The state may or may not be observed. Many of the models we'll think of allow us mortals to observe the state, but in case not, you can have an additional equation, which we'll be interested in today, is the observer equation. So this is the part of the economic system that we as observers can actually see. and it may be equal to the identity matrix, but generally it's not. So think of G as being this observation matrix, part of the observation equation or the observer equation, which translates the state vector xt into observables yt. So yt could have dimension k by 1, and k could be less than n, or it could be equal to n, and basically is translated into maybe linear combinations of xt. A good example might be we observe the sum of two components, but not their individual elements, or their difference. So these are all sorts of different vistas of expansion of the purview of the state space by just simply redefining things along the G matrix. And in the problem set, we used the Kagan model and tried to describe the Kagan model using this feature. We could also use this observer equation to model the new Keynesian Phillips curve. Okay, so nomenclature is clear. Xt is the state vector at time t. X0 is the initial condition, which is given to us. We can't choose it. Okay, it could be some arbitrary initial condition that we have to deal with to start the problem. And A0 is the transition matrix, called often, because it describes the deterministic transmission of xt into xt plus 1. Call CT the transmission matrix because it involves the transmission of the shocks. And the shocks that are fundamental to the model and are not explained by the model, they're fundamentally outside the purview of the economist's analysis, are these random shocks that literally could be the president of Russia wakes up in a bad mood, the president of the United States catches a cold, there's an earthquake in Peru. These types of shocks have economic impact in the current period. And the rest of the model is just a matter of how these shocks are transmitted over time. Now, through creative definition, we can always put lagged shocks into the model. With appropriate bookkeeping, we can redefine A0 to do that, but we can't make it an infinite lag on previous shocks unless it's implied by a geometric sum that falls out of the A0 matrix. So this is one of the restrictions of the state space model, but we won't have to deal with that in the next in the lectures that come up. Now these fundamental shocks we're free to define them as we please, but we want them to be somehow have plausibility. So we think of these shocks as being disturbances that we haven't anticipated, but might have to do with the weather or with monetary policy having a random element, or maybe the government has certain political influences that we can't or won't describe in our model. And we need to normalize those shocks because the C matrix, the transmission matrix, automatically scales up those shocks arbitrarily in a linear way to make them fit in the model. So it's convenient for us to choose a normalization that this omega shock has mean 0, for example, and that it also has some restriction on its variability, or that its variance is normalized to 1. So these are 3 examples that are given in Lundquist and Sargent on how to work with that normalization of the fundamental shocks. And one is just to say that the omega vector, remember, omega does not have to have the same dimensionality as the state vector at all. It could be much larger. You could have many, many shocks that are hitting the system. It may not be easy to identify the transmission matrix, but it might certainly exist. And we'll assume that this omega in the A1 assumption is that omega is identically and independently distributed, and it's a normal covariate. So the first 2 moments completely summarize the distribution, and think of it as having a covariance matrix equal to the identity matrix. So we've imposed orthogonality of the fundamental shocks. They're not correlated with each other, but they could be correlated with each other in their impact on the system through the C matrix. Because the C matrix implies that both shocks affect two different variables that will induce a correlation that will look as if the underlying shock was somehow moving together, but in fact it's just a linear combination of orthogonal elements. Okay, so it's a normalization. The normality assumption would be A1, fairly strict, but usually quite useful normalization. A2 is a little bit less strict, a bit less imposing. It's a so-called filtration assumption, which says basically that we're going to make omega t plus 1 have a mean zero conditional on all information available in period t. And we'll call that information set J, and J evolves over time as per the increment of new information that is contained in omega. So there's no new information, there's no forgetting, we don't drop pieces of the information on the sidewalk, and we use the initial condition as well, okay? And given that information, JT, the conditional expectation of the outer product of the omega vectors, over time, is constant and equal to the identity matrix. So it's an alternative normalization, a bit less strict, a weaker assumption than A1. Finally, we could assume A3 as an alternative, which is simply that the mean and the variance of this omega vector is equal to 0 in the identity matrix respectively, but we won't impose anything on the higher moments. So this could be certainly a weaker assumption than A1. So there might be higher moments that are interesting, but they're not going to be useful for us in this particular setup. Okay, so an unconditional expectations concerning the first and second moments of this random vector omega t plus 1. Finally, we would assume in A3 that the autocorrelation or the autocovariance function is 0 at all leads and lags of this variable. So for all practical purposes, it's like white noise, but with no restriction, with the only restriction being that the variance of this covariance matrix over time is constant. Okay, so given that format, we'll go into some of the interesting aspects of the state space. And the first one I'd like to talk about is the Kalman filter. But to get there, we'd like to really understand what a linear projection is under these conditions. So this is going to require a bit of abstraction. But if you think about it, geometrically, we can always think of a three-dimensional space. We can picture it. And x1 would be a two-dimensional vector, and x1 would be a two-dimensional vector that form the basis for a plane. And then y is a random variable or some random variable that need not lie on the plane. So it's just in a three-dimensional setup, it would be some point out there that does not lie as a perfect linear combination of x1 and x2. What you see in this geometric representation is the question, how much of y can I account for using x1 and x2? And if you just consider dropping a orthogonal line to the plane so that all lines in the plane are perpendicular to the ray or to the line formed by the point of projection to the point y, this would describe all vectors in x1 and x2 that have dot products or inner products that are equal to 0 with that projection, or that the remaining component of y after you've subtracted the linear combination of x1 and x2 is perpendicular to the plane formed by x1 and x2. We call this this representation of y as a projection of y on the plane, and what's left over is sort of the unexplained or unaccounted for component. So literally, you've decomposed the vector y into two parts. One is the part formed by b1 times x1 and b2 x2. And I think we've got a typo there too, but you can probably see it. It's pretty clear. And the residual, which would be y minus this linear combination. So that's kind of what a regression analysis does in general. But now think of these x1 and x2 as being a very high-dimensional vector. You can still, even though you can't visualize more than 3 dimensions in your mind, you can still think of these two vectors consisting of points in a high-dimensional space. And if you have 2 of them, they certainly form a plane, and that plane is a valid representation of y, and there's going to be a valid part of y that's not part of that representation, and that would be the orthogonal residual. Okay, so that type of decomposition is not limited to 2-dimensional or 3-dimensional representation. So you can think of if you think of x1 and x2 as being time series with, say, maybe 300 observations of time for GDP growth and for unemployment, then you could use both of those to somehow explain a third variable like the inflation rate, explain it in the sense of accounting for its variance, and then the distance of y to that plane is simply is 1 minus the r squared, the representation of 1 minus r squared, how much of the variance we can't explain. Okay, so linear combinations are a fantastic and fairly useful way of trying to represent things we don't really understand very well. So it's not necessarily a model in the economic sense, but it's a way of accounting for variance, and it's used quite a bit. So if you think about applying this to a lot of data, not just 2 data points or 300 data points, maybe sort of, 30,000 or 300 million data points. It's all about still minimizing the distance of this projection. So going back to the picture, it's a way of trying to make the distance of y to the plane as small as possible. And that's called the least squares problem. Okay, it's simply choose in this case, the pair of coefficients beta 1 and beta 2 that make the expectation of, and this is letting the number of data points go to infinity basically, or just an unconditional expectation of pulling 300,000 data points, what would be the expected value of the distance minimizing choice of beta 1 and beta 2 given that draw of the data, and then doing that many, many times and seeing how that works out. Well, this is just simply the least squares problem. Okay, so we're just trying to make this sum of squared residuals as small as possible. And you could indeed let x1 and x2 be anything you want. Okay, so think of this beta x, this linear combination. It doesn't have to be 2 variables, it could be several. It is an estimate of the least squares projection, and when you take the first order condition of that problem, it involves each element of the beta vector taken severally together. It just basically imposes as many conditions as first order conditions in this problem that whatever we can't explain has to be orthogonal to the variables we're using to explain. So it's almost a trivial definition of what least squares is, but the point is it's what we call a moment condition. We're imposing that this moment theoretically equal to 0, and in practice we'll choose whatever beta we need to make this set of moments as close to 0 as possible. Okay, and if we, under certain conditions, if we have lots of x's, we can make this really small, but of course, we're not doing any economics here. We're just trying to maybe even forecast in a stationary environment. Might be a good way to forecast the future evolution of these variables. So if we rearrange that first order condition using the law of iterated projections and some matrix algebra, we can see that it's basically a condition that defines beta as an optimal choice given a bunch of expected values of matrix products, which we call moment conditions. So we're basically asserting, and this is also in Lundqvist and Sargent, that this beta that solves this problem is basically going to be a function of two moments. One is effectively the second moments of the x variables that we're using, the explanatory variables, and the other is the moments formed by the y variable that we're trying to explain. Okay, so many of you have taken simple econometrics. The expression looks very similar to this. This is just because of the conformability of the matrices in this problem. Following Lundqvist and Sargent is a bit off the wall. When I took econometrics from Grillicus using tile, we didn't write the matrices down in this particular dimensionality, but it doesn't matter. It's either k by t or t by k. You get the same answer. The point is, beta times x, where beta is the solver of this problem, is the least squares projection of this variable which we're trying to sort of account for on the elements of x. So if we have the situation that we've been sort of assuming for all along, that we have an ergodic process, so with probability 1, we're going to visit all the states that are possible. The law of large numbers would be reassuring that if we base estimates of beta, if there is a beta, okay, if the data generation process does imply some beta, then if we get more and more data, we'll get close to the beta. Okay, so this is kind of what the Kalman filter is striving to do, because in the Kalman filter setup, especially the one we're going to talk about today, in a stationary environment, you're constantly acquiring more information about something you'll never really understand or learn about, but you're getting better and better at it over time. Okay, so the Kalman filter is probably it's probably one of the leading applications of the state space representation, and I'm just going to make a simple modification following Lundqvist and Sargent. We'll use the same notation. So we've got the AOC set up. And now we've got this observer equation with a slight hitch, which is we cannot observe the state even in its linear combination perfectly. So we know there's a G out there that linearly combines elements of X to make Y, but this observation is polluted by some noise. And the noise is, we're going to call this nu. Nu t is the noise that makes the signal imperfect that we would normally get from G times xt. Okay? And we'll have to add, again, a reminder that the notation is such that y is a k by 1, and this noise vector is a k by 1 vector. So think of this noise as just being some orthogonal element of the world we live in that just makes it very, very difficult, or even impossible, even nearly impossible, not completely impossible, makes it very difficult to observe the true state, even if we know how G is constructed. So we need to make some assumptions. So Kalman and others go with the normality assumption. We'll assume that the underlying omega is normal, so we'll use the A1 assumption, and we'll use a normality assumption for the nu, and we'll assume that nu is orthogonal to the omega, so the signal is really a pollution of the model, and we'll assume that we know the covariance structure of the noise. Okay, so all these assumptions can be played with, but we'll just take this as a sort of a benchmark version of the Kalman filter. So we have this additional randomness which makes life difficult for us, and we have to plow through. Now, of course, a very important assumption is that we know G. So we have enough knowledge of the system is that we know how the system would normally combine elements of the unobservable state vector, or possibly partially observable state vector, into the observables. We also know what R looks like. So going back to remind you what R is the covariance matrix, the outer product, the expectation of the outer product of the noise. Okay, so we have some prior information which we could also estimate, so the Kalman filter can be used in an estimation routine, but there has to be some sort of stability in this noise process that we can rely on in this basis. So we're going to call YT the signals, and the hidden state, we'll call it XT. Okay, so we won't observe anything. We'll keep it as open as possible. And we're going to call nu the noise that confounds the observation of the state. Okay, so that's a good setup for us today. So the idea is, how can we go through life observing YT from t equals 0, t equals 1, t equals 2. As we move through time, we get more and more observations of YT. We know what the model looks like fundamentally. We don't know what XT is, but we have an idea of what the signal's being polluted by a noise that we understand. And the question is, can we use successive observation of YT over time to get a better and better estimate, which will never really be perfect, as we move through time, get a better estimate of the state vector XT. Okay, so that's basically what Kalman filter is about. The Kalman filter is a really useful object. It's used in engineering and other applications in applied physics and signal processing, etc. We're using it in economics. It's used a lot in econometrics, time series econometrics especially. It's also used in Bayesian estimation methods. Okay, so we're going to take the assumption one, that, and I already said this, that the signal and the noise are orthogonal to each other. Okay, so this is an orthogonality condition that also holds in terms of leads and lags. So it's basically saying the signal is not something that helps us, the noise is not something that helps us get a better beat on the signal. Okay? We'll assume that's true for all leads and lags. So the normal distribution assumption can also be made for the initial condition, which we can't control or observe. In other words, we start with an assumption about what x0 is and how it's distributed at the beginning, and that's going to sort of drive it's going to be the initial kickoff of the model. We'll assume that the initial condition on x0, the state, is normal. That is, x0 has a mean x0 bar and has a covariance matrix sigma 0. Okay, so that's an assumption. And that means that y0, given the model, is also normally distributed because y is just a linear combination of the elements of x. Okay, so if we know the covariance matrix, we know the transmission matrix, the observer equation matrix G, then we can basically take the assumed variance covariance structure for x0 and make a similar judgment on y0. Okay, so this is all known to us because we know what G is. Okay, now the observer, or the decision maker, as she goes through time, is allowed to observe successive elements of this realization of YT. So over time, in every time t, the observer is allowed to observe YT as t goes from 0 to infinity. But the observer, she never gets to look at x. Okay. We also assume that she knows the structure of the model and she understands everything that I'm talking about, and at least intuitively knows how to solve this projection problem. Okay, so she'll start as an initial guess with her obviously best guess of x0 and its covariance matrix sigma 0, because she kind of has to start somewhere. So she'll start with that, and then she'll move through time using her observations on y to see if she can do better. Okay, and again, The assumption is that she knows everything else. She knows A0, she knows C, and she knows about R, and she also knows about G. Okay, so she knows how the state is translated into the observer observation. Okay, so start the game. She observes Y0. She'll never get to observe X0, but she knows what she thought her best estimate of Y0 would be, which was G times X bar 0, or X0 bar. And that difference is kind of a mistake, new information, something. How is she going to interpret that? Well, the idea is as she moves through time, she will use that information in the period 0 and successive mistakes that she makes, because she'll always make a mistake. She'll have a best guess of what t should have been, and given her best guess of xt, and then she'll write down her mistake, and she'll adjust her forecast rule as she moves through time, and I'm going to show you how she does that in a second. Think of it as using more and more information to compute or to second guess the model as time passes, is the best way of processing the information as she goes through time. Okay, so she's going to be upgrading or updating her estimates of X and sigma as she passes through time. So it won't be just updating her guess of the state. She'll also be updating her guess of the variance-covariance matrix of her mistake. Okay? So it leads to the following 4 equations. The first one is the computation of the error. Basically, she had her best guess G times X bar T, and she has an observation that she can observe. She computes that. That's her mistake, if you like. And then you can imagine she could adjust a couple of things. First off, she'll adjust her guess of the state tomorrow based on what she observed today and what she thinks is the state today. So that would be the third equation. So you can see that xt plus 1 bar is equal to a0 xt. X0 t was her mistake. Was her guess of the state in period xt, which was, again, we don't know if it's right or wrong. We just know what the observer equation says. But then she's going to have to look at her mistake with respect to what she thought yt would be and adjust it. And that's what kt is. Kt is called the common gain. It's like her little adjustment of her guess of the state given how far off she was. Okay, so this is a great way of thinking about inflationary expectations, by the way. I mean, people could use the Kalman filter. You observe the price level. Does that mean that the price level tomorrow will be higher or less, given your expectations of all the things that drive inflation? What will be the adjustment? And KT is sort of like how far of a step you want to take. And this KT is a very complicated matrix because it's multiplying a vector, okay, a vector of the deviations of the observed value of y from its predicted value, and therefore it's going to involve a lot of things. It's going to involve the structure of the model. It's going to involve the presumed forecast error, which is R. So think of R as sort of the noise that we know is making it difficult for us to observe the true state anyway. So the bigger that is, the larger you're going to discount the observation. That's why it enters, if you like, if you think about it as division, and it's like multiplying by the inverse of R. R gets bigger, you end up scaling down the Kalman gain. And then, of course, the ability of the model to translate the shocks into the state depend on both A0 and G. So that would explain the size of the Kalman gain. The stronger the association, the bigger G, the bigger A, the larger the Kalman gain will be. Now, given this Kalman gain, we will learn something also about the covariance matrix of the state as we think of it, because we don't know what that is either. We have to sort of adjust our guess, and the way you adjust it is you take C and C prime, you scale up the noise by the amount of, by the Kalman gain, and you basically add this to the previous estimate of the covariance matrix that derived from the previous value. So you think of the sigma t plus 1 as being updated as well by the model. And this is a fairly standard version of the formula. So see, over time, as you move through time, you get more and more information. The precision on sigma will increase, and sigma will basically reflect that precision. So the Kalman filter is used a lot in economics. It's used more in natural sciences and engineering. It's in economics, we use it in econometrics and time series econometrics. It's also used in models when you think about people learning. So if you're on the job market, you have a certain a priori view of how well you can sell your labor in terms of an expected wage. Your reservation wage may be based on that expectation, which may be patently unrealistic. And maybe if you draw a couple of bad wages, you might scale down your estimate of the mean of the distribution of your wage offer distribution. You may scale down the mean, and that's kind of what the Kalman filter would tell you how to do if you knew that the environment applied involved the same principles that have been invoked here. It's also useful anytime that agents measure things with error. And we can embed it in models that involve any sort of speed of convergence which is related to changing expectations. So again, to use suppose agents in this world we live in wanted to look carefully at the price of energy, and there's a true state of the price of energy, and that involves maybe the long-run fundamental determinants, whether certain suppliers will continue to supply energy, whether we'll have new energy sources. But from week to week, we have financial influences. Maybe the interest rates affect the price of derivatives that affect the spot prices for these energy sources. All these things could be thought of as noise that confound or conflate the signal that people are trying to understand. Rudolf Kalman was quite brilliant in applying this, and much of this work has been used in rocket science, and literally rocket science. Good, so I mean, you can use that, and I hope you do. Hope you remember next semester when you do Bayesian estimation of models, because the Kalman filter is one way of computing the likelihood function. Given some initial conditions and some structure of the model, you can construct a likelihood function that you can go on to maximize. Okay, so the next part of this lecture will involve a very general set of mathematical steps that you would take to evaluate a linear quadratic objective. So what do I mean by that? Well, we often deal in economics with expected values of infinite sums of some object that we're trying to make as big or small as possible, maximization, minimization problems. And often those problems can be attacked either using the Lagrange multiplier approach, especially if they're not linear quadratic. You can use this a much more general approach. We used it already last week. You can also look at this infinite period problem as you can express it under certain conditions as a two-period problem. The two-period problem is two parts. One is if I want to maximize something that has an infinite horizon, I can think of it as maximizing today's value of some return function plus the maximized value of myself taking the decision tomorrow, my own optimized value tomorrow. So if you can collapse the problem to a two-period problem, it turns out to be quite easy to deal with. You need to assume that this value function takes a certain form, that it's differentiable, et cetera, but it's an alternative to using Lagrange methods to solve these problems. Okay, so the idea is you know you're going to behave optimally tomorrow, and you know that you're behaving optimally today, and therefore your optimal behavior today must include your envisioned effect on the optimized value of whatever you're maximizing tomorrow, and that doing that properly is just a recognition of that yourself, your deciding self in the next period is the same, is going to make the same policy decision. So it's kind of implying a policy, time invariance of policy. Okay, so the policy will be a function of the state, but not a function of time, calendar time, or something like that. So sort of a time consistency outcome. So one way to motivate that is to go back and think about the linear quadratic objective, and think of that as possibly like a welfare loss, a parameterization of some utility function, or the loss function to a monetary policy maker, or to a government, or to a firm trying to maximize profits. So all these things involve expectations of infinite sums of some function. And next week we'll actually use the value function approach directly, but just to get things rolling, I'm going to use a trick that Lundquist and Sargent use in their book, which is like a warm-up. I'm just going to manipulate an infinite valued sum. Using the AOC framework, I'm going to collapse that into a simple function of the state vector xt. So even though I'm thinking about an infinite sum of functions of xt into the future, the very nature of the state space allows me to collapse that function and the linearity of expectations, and that's all I need basically is to write this problem very compactly. And I think showing this first and then next week we'll do the other problem is a great way to get some intuition on what I'm doing, okay? So here's the objective for us. I'm going to call this alpha t using the Lundquist and Sargent notation. It's the expected value of an infinite sum of discounted values using the discount factor beta less than 1 greater than 0 of a quadratic form, which is, it's basically, think of it as a sandwich, using the state vector as a sandwich, as the bread, and y is the meat. Y is sort of the set of constants, a matrix that weights the elements of the state vector xt in any arbitrary way you like, creating linear combinations of various quadratic terms, products of xt, elements of xt with itself. So think of this as a quadratic form as a scalar, so every element of that geometric sum is a scalar, and it's the weighted inner product of xt plus I goes from 0 to infinity, so, and y doesn't change, y is constant. So y can sort of be the linear quadratic approximation of a very complicated continuous function. It could be a utility function, it could be a profit function, it could be central bank's objectives, it could be government trying to get reelected, et cetera. Okay, so we'll define this so that we'll eventually want to be maximizing or minimizing something like this. And if it has a linear quadratic form, then there's going to be a unique maximizer, so we can really use this as a way of fixing ideas on a much richer class of problems. So these quadratic forms are going to be important to us. And yet we know that this problem is already very complicated, because I need to form an expectation of xt plus 1, an xt plus 2, an xt plus I for I going all the way to infinity. And I need to make an expectation of that product. How am I going to forecast xt plus I? Well, the state space gives us the means to do that, and that's the whole point. We don't have to literally construct a forecast of each one of these xt plus I if we know that the world obeys the law of the state space. We have a linear quadratic setup, so it turns out it's an easily manageable problem. Okay, and that's what I'm going to motivate. We're going to try to write this object using the state space only as a function of the current state, only of xt. So I'm going to write this incredibly complicated looking object only as a function of the state. Okay, so that's the current value of the state is sufficient. Remember, the state space allows us to write even a very complicated linear world by making xt somewhat more complicated, involving lags, many lags if you want. And this is already quite an achievement. And then to be able to do this will be really amazing. Okay, so we're going to do, following the book, we're going to follow them and just say, we have a feeling that whatever we find is going to be a linear quadratic form. Indeed, if there is a representation of this alpha in the form of a quadratic form of xt, then it's going to be unique, and I should be able to solve for it. In fact, if I can guess that it takes a certain form, and I can actually use that guess to help me find that form. So this is the so-called guess and verify approach. Okay, so using the linear quadratic setup is essential to solving this problem. We'll guess the form of alpha t. Okay, remember alpha t is a quadratic form of xt, and the reason why there's a subscript t on alpha is because it has this component xt. It contains xt. We're going to assume that it takes a quadratic form. So we're going to assume that it's this new matrix V, which has nothing to do with what I had before on the Kalman filter. This is a square matrix that's conformable, so it's n by n. So if that's the case, if our guess is correct, then the left-hand side of what we had before has to be in some sense compatible with the right-hand side, which was the maximization. Okay, so the left-hand side being the sandwich using the meat V plus a constant. So I didn't mention the constant, but there's a constant you need to scale up to make this right, because there might be a constant on the right-hand side. And there's no maximization taking place. I'm just going to try to rewrite the objective, which is an infinite sum of expectations, okay, or the expectation of an infinite sum of discounted sum of these quadratic forms going into time that we already understood involving y. Okay, so if I make this guess, then the left-hand side and the right-hand side have to be equal. Okay, and it turns out that I can exploit my assumption to tickle this out of the model, because I'm going to lead the quadratic form on the right-hand side and insert it, call it alpha t plus 1. I'm going to insert it into its definition, which is the once leaded version of this expected value of geometrically weighted sum of quadratic forms. So think of this as the first step, breaking up the right-hand side into two pieces. The first piece is the t equals 0 piece, or I equals 0, excuse me. And then the next part is the discounted value of the same object in t plus 1. Okay, so starting in t plus 1, we do the same exercise. But it turns out that's exactly what alpha is in t plus 1. Okay, it's the expected value of the quadratic form involving xt. So I already have the recursive characteristic in line 3. Okay, so the left-hand side involves the right-hand side leaded by one period, or the right-hand side involves the left-hand side leaded one period, and therefore I can substitute and I can try to match these points. Notice I only have the expected value of the problem in one period. So let's take the state space and substitute it for xt plus 1, and then just multiply it out. Because if I can do that, then I have a weighted inner product of a vector that has two components. So I'm going to have four components altogether. If I multiply them out and just stare at that for a while, I still have sigma. Sigma is a constant. I'm taking the expectation conditional on time t of 4 objects plus a constant. So I can distribute the expectation over the sum, because that's what we can do with a linear operator. And we know that xt is orthogonal to omega t plus 1. So pass the expectations operator through this sum, take expectations of the individual components, and use the orthogonality condition to make terms 2 and 3 disappear. All that's left is the first term and the second term. The first term is in the information set in period t, so it's the same thing as xt prime times a0 prime times v, or I think I called it nu, a0 xt. That's a deterministic part from the perspective of period t. It's predetermined. And then the fourth term is the inner product of, if you like, of omega t plus 1 prime c prime with itself, with a weighting matrix nu in between. So that's the third term. So we basically, we've killed 2 terms already. We still have to match, we have to verify what we guessed. So we'll have to solve for the nu and for the sigma. That's the whole objective of this exercise. But we've moved really quite far already, because we already know what xt is. Xt is basically this inner product with a new weighting matrix, which is y plus beta times a0 prime nu times a0. Okay, so that's already quite amazing. We're going to be able to match that with nu and solve for it, but let's proceed a little bit slowly, because we still have this last term. If we want to match the constant, and remember, this is all basically a scalar. These are scalars, so this is a number, this is a scalar number, this is a constant. This scalar involves a quadratic form involving xt. This is also a quadratic form involving xt. This is a constant. So how do we evaluate this? This is easy. We're going to match this one with this one, but we still have to figure out what that thing is. And we're going to use an arcane trick from econometrics, matrix algebra, to help us do that, because we know that thing is a scalar. Okay, it's a 1-by-1 matrix. But it turns out evaluating that thing is not so easy, because we don't know much about that inner product. Effectively, it's the inner product of the weighted inner product of c omega t plus 1 with itself, using nu as a weighting matrix. So how can we tickle out the answer? Well, it turns out that if you remember from your econometrics, the trace of a square matrix turns out to be can be understood. If that square matrix is the outcome of the product of 2 matrices A and B, then it turns out that the trace of that matrix is also equal to the trace of B times A. Okay, so again, they have to be conformable such that AB is a square, so BA is a square, but they don't have the same dimension. But it turns out that, again, this is a result that many of you we'll never look at again, but it could be useful in your future. It just says that this is always the case, and you can verify it if you want, but it's trivial in the case of a 1-by-1 matrix, because the trace of a 1-by-1 matrix is equal to the number itself. If it's a scalar, it's just equal to a scalar. But we had a 1-by-1 matrix. Okay, so it turns out that we could rewrite the trace of this 1-by-1 matrix as the trace of a rearrangement of A and B. So defining A as omega t plus 1 prime C prime V, and then, omega t plus 1 prime C prime, and B is V times C omega t plus 1, taking the transpose of that shifting of A and B would lead to what you see in the third line, which is the trace of, and it's still a constant, right? It's still a constant. It's basically the trace of an expectation that we can take, passing the expectation through the constants. So it's an expectation of the outer product of omega, which we already know is the identity matrix from the assumption we made already. So the third line results from the second line, which results from the result of matrix algebra. Okay, so we end up having V times C transpose, and that trace has to be equal to the trace of what we had at the very beginning, even though V times C transpose is not a 1-by-1 matrix at all. Okay, so that's the good news is we can figure that out. So if you tell me what nu is, I can tell you what that object is. It's a scalar, and we can use that to help us find what sigma is, because sigma is the undetermined coefficient. Okay, so matching terms, first we need to get nu. So to get nu, we have to match left and right. We're going to have to match nu on the left-hand side equal to y plus beta a sub 0 prime v a sub 0. How do we find nu there? That's what we're going to have to do next. And once we find nu, we can go into the second formula and compute sigma directly, because we know what beta is, we know what C and C transpose are, and we know how to do a trace. Okay, so that's good news. How do we find nu? Well, remember, nu is a matrix equation, so it defines a matrix on the left-hand side. It doesn't have a solution using matrix algebra. You have to use numerical methods. Okay, there's lots of easy numerical approaches. If you just look at it long enough, you see that nu on the left is a function of nu on the right. So if I give you, if you make a good guess of nu, you can plug it at the right-hand side. We know what y is. We know what beta is. We know what a0 is. We can compute a nu. And the nu is the seed for the next step. So you take the nu and plug it on the right-hand side and generate another third round of nu, and keep doing that until nu stops changing. And that's a very simple way of understanding an iteration on this equation would give us, under certain stability conditions, and if A0 is a stable matrix, it does work, you can actually grab that thing using simple MATLAB program, or you can ask a sophisticated numerical solver to do it for you. Okay, so we can solve for a value of nu. Once we get that matrix nu, remember that was the assumed form of the quadratic form, because we basically assumed that to get started. That was the whole point. We took a guess. Okay, so once we get the nu, we can go back and match to get the sigma. Sigma is just the trace of VCC prime times beta divided by 1 minus beta. That's just the level of this quadratic form. It's just a constant. The dependency on the state vector is is independent of sigma. Sigma is just a level effect, okay? So we've basically, we've solved the problem, we've verified, we've guessed, and we've verified that the guess is correct. You might want to think about this problem as being related to a policy function. So in some sense, if we know what the optimal policy reaction is to the state vector, and I'll show that in the next lecture, you can actually embed that into X as well and end up getting a convenient interpretation is that this quadratic form, when you embed the policy rule, is like a value function. It's the optimized value, given the state of what I can achieve. It's the best value of the objective that I had, the objective being this some sort of present discounted value of a weighted, geometrically weighted mean of the sum of the return function, or the value function would be that interpretation. It would be the maximized value. So that's really useful. I will try to motivate that with a couple of lines, and we'll stop. Okay. So suppose the policymaker today assumes that whoever the policymaker decision is tomorrow is going to choose her optimal policy based on the state. Okay, so suppose her optimal policy is U, and UT is simply a linear combination of the elements of the state vector X. Okay, so UT is equal to some matrix F0 times XT. And the reason why that minus sign is there is I'm trying to follow the notation in Lundquist and Sargent, which take the context of a minimization problem. And of course, we're maximizing things in the value function world. But if you take the minus of a thing you want to minimize, you're going to get a maximization problem. So just think of this as a notational trick to keep things consistent. Now, suppose the state is partially controllable. So the policymaker tomorrow, whoever's choosing UT today, can influence XT plus 1, the state tomorrow, by means of this equation double star, which says that XT plus 1 is the deterministic dependency on the state, XT. It's a function of the control via B, and of course the transmission matrix times the shock. Okay, so if we think that the policymaker is choosing UT in a way that's a policy, even if it's not optimal, if it's just choosing it according to a policy, then we can collapse this double star equation into the AOC form. Now you see why it's called AOC and not AOB, because B is leaving a little bit of space for optimal policy, or any sort of policy. Any sort of policy means basically that this new A0 matrix is a function of the original A matrix minus B times the effect of the policy, or the relationship of the state to the chosen policy. Okay. Now, if this policy rule is actually optimal, then you can think of the quadratic form we just described as being optimal policy. That is, the quadratic form, the present discounted value quadratic form, can be thought of as a value function. Okay, so I'll leave this in the air for next time because we're going to talk about it in detail. But this value function approach is an alternative in, as you can imagine, in 2 periods, dealing with the much more complex idea of dynamic optimization over an infinite horizon. We're collapsing the problem into 2 periods. Basically, what can I do today, and what is the best I can do tomorrow, given the state that I have influenced somehow today, tomorrow. Okay, under a lot of conditions, those 2 problems don't change in their character. They only depend on the state, and those are the kind of problems that we want to care about, at least in a stationary environment, in the sense that the policy rule is independent of calendar time. It only depends on the state vector xt. And we don't have to stick to the linear quadratic form or the linear quadratic framework. We can actually extend this to think about much more complicated environments with nonlinearity and the like. Okay, so keep these in mind. Projection, signal to noise, signal and noise, and of course the the signal-to-noise ratio, which we didn't talk about, is very important. It's kind of implicit in the Kalman filter. The bigger the noise, the less you regard the signal, because the signal plus the noise is kind of less informative, and that's actually part of the Kalman gain result. We talked about the filter and the gain. Take a look at that. Again, the notion of linear quadratic form is ubiquitous in macro. It's a great way to get an initial understanding of what's going on. And thinking of the linear quadratic form as a return function would allow us to collapse a complicated setup using the AOC framework. If the world is indeed linear and amenable to state space analysis, would allow us to write an objective, or just any sort of sum of infinite sum of discounted values of that quadratic form in a way that only depends on the current state. You can use guess and verify to find that representation, and we can think of it as a value function if the state is being controlled in some sense optimally in subsequent periods. And we can call that optimal policy the policy function. We'll do all this in detail next week. And this is why the book is called Recursive Macroeconomic Theory. It basically runs on this notion that what we do today and we think is optimal should be based on the same type of principles that we'll use tomorrow. And if the world is stationary, it will be the same sort of policy rule. It will only depend on the state and not on the calendar period or any other time-dependent variables. Okay, thanks a lot for your attention, and look forward to seeing you next week.